So I'll start the mini recap lecture for the second half of chapter 1. This is Math 95, and it's 6/30/2025. First topic actually pops up in section 1.2, but I hadn't fully covered it last week, so I want to cover it now, which is independent and dependent variables. All right, so we often use mathematical formulas. Let's remember our 4 ways of representing, this should say numbers, mathematical ideas, and moving between the different ways is one of the skills that I want you to work on. And we often use mathematical formulas to represent physical applications. And the way we do it is we imagine 2 variables where one variable affects the other. For example, when driving a car, the speed at which you travel affects the miles per gallon that the car gets. So here are 2 variables, the speed at which you travel and the miles per gallon that the car gets. And the speed affects the miles per gallon. We would say the speed is the independent variable. It's what you choose. And the miles per gallon, which I'm going to abbreviate as MPG, is the dependent variable. So this would be a words or a verbal representation of this idea. Now, if I had a formula, I might say the miles per gallon is, let's say, starts off at 50 miles per gallon minus 1/10 times the speed. So you choose your speed, and that tells you what your miles per gallon is going to be. And if I label miles per gallon y, and I transform this into an equation, it'd be y equals 50 minus 1/10 x. Speed is x. So this means generally in a formula, the y variable is the dependent variable. The x variable is the independent variable.
Distance would be another variable or not?
This one doesn't talk at all about how far you're going.
Okay.
It's just talking about how fast you're
Okay.
going. Yeah, so the faster you go, the lower your gas mileage. Now, if we were to put this in a graph, we would say miles per gallon is a function of speed. And here's my speed, and here's my miles per gallon. It starts at 50, and it loses miles per gallon as my speed increases. So again, we can identify the independent variable almost always going to be on the horizontal axis, the x-axis, and the dependent almost always on the vertical axis. That's just a convention that mathematicians came up with a long time ago. And finally, in a table, we usually put the independent variable on the left and the dependent variable on the right. All right. Any questions about that idea? All right, so section, let me grab it over here so I know what the name of that section is. Section 1.3, equations of linear functions. Hello. So many physical applications can be modeled with a linear function. And the key characteristic of a linear function is in a linear function, the dependent variable are y changes by constant addition. In other words, when the independent variable x increases by 1 unit, the dependent variable y will add a fixed number each time. And add could also be subtract, as we think of as addition and subtraction as being two sides of the same coin. So we're going to look at all four representations of linear functions. and figure out how to build those equations. We'll start with a verbal representation of a linear function. Example, I have $20 in my piggy bank. Every week, I add $3 to the bank. That's a verbal representation of a linear function because every week I add a constant amount. Here, the independent variable is weeks, and the dependent variable is the money in the bank. And that's a completely valid way to represent this situation mathematically. Now, if we wanted to represent it with a formula, we could say money will be my y, and weeks will be my x. And so the amount of money I have, y, is going to be $3 times however many weeks I'm counting, plus the 20 I started with. And often when we do a formula, we don't put the units. We're not doing the little dollar sign and things like that. But it needs to be understood if it's a situation that this y is money in dollars and this x is weeks. And I put a dot there to show the multiplication. Most of the time, when you're multiplying by a variable, you don't do a dot, you just do 3x plus 20. So here's our symbol representation. Or formula. This $3, the 3 is a constant addition, rate of change. And if you haven't seen it be defined before, we call it the slope of the linear function. And the 20 is the initial or starting value, right? Because I start with $20 in my piggy bank, and we call this the y-intercept. Every verbal representation of a linear function should have some kind of y-intercept in the sentence and should have some kind of slope in the sentence. And with that information, you should be able to convert from your verbal representation to your formula representation, which can make doing some math a little bit easier, right? If I wanted to know how much money I have after 19 weeks, doing it this way, I could do it. Doing it this way, probably a little faster. 3 times 19 plus 20. Calculator, boom. All right, so let's look at the graphical representation. X is going to be, what was it, weeks? And Y is going to be money. I'm going to start with $20. The scale I put like this so we have some space. And then we're gonna count by weeks. 1, 2, 3, 4. And each week I'm going to increase how much is in my piggy bank by $3. And so the dots, probably if I'm putting it in once a week, I wouldn't actually have this line connecting all the points, but we can visualize it this way. This is a line, which is why we call it a linear function, because when you have a graphical representation, it makes a straight line. The 20 is the y-intercept because it's where the line touches the y-axis. That's why we call it the y-intercept. This is exactly right. Yep. Yeah. I'm going to write that down. No. Questions that come ahead are fine. Always happy to answer it. Yeah. Yep. The slope is how much the y increases when the x increases by 1. The slope is 3. So slope, another way we describe slope is rise over run. It rises 3 when the run increases by 1. And the table form would look something like X and Y. When my weeks are 0, my money is 20. And then as my weeks increase, each time my week increases by 1, my money increases by 3. You can find the y-intercept by looking where the x value is 0. And you can find the slope by looking how much you add each time you increase x by 1. So all 4 of these representations can show you exactly how a linear function works. Sometimes one's going to be more useful than the other. And the very most general form for writing a linear function is y equals mx plus b, where m is the slope, b is the y-intercept. So what if you're given a situation and you're asked to find the slope and the y-intercept, or maybe you're asked to find the equation? So maybe you're given a verbal representation and you're asked to find the equation, or a graphical representation and they're asked to find the equation, or a numerical, because sometimes the equation can be the most simple way to work with your function. Finding equations from other representations of linear functions. Let's start with verbal. This is just actually going to be a recap of, or like another example of what I just did. A tiger is resting 35 meters from its wading pool at 12 o'clock. It gets up and walks toward the pool. Every second, it gets 2 meters closer. to the pool. Write an equation for the distance starting at 12 o'clock, from the distance from the pool. Starting at 12 o'clock. And I'll give you a chance. I know I write very fast. I'll give you a chance to get that down. It's waiting pool. Sometimes I write faster than I should. So if you have to write an equation, different functions have different forms of equations. We're going to study exponential equations, and quadratic equations, and logarithmic equations or functions. We're going to study a lot of different types of functions in this class, and each function has a different form for its equation. So your first question should be, if I want an equation, what type of function is describing this situation? And you get that from the context clues. Every second, it gets 2 meters closer. That's a constant rate of change. Every second, it gets 2 meters closer. That is changing by constant, in this case, subtraction, which tells you it's a linear function. Now, some of you, as you go through this process, you may feel like you're skipping these steps, which is great. You might look at that and be like, aha, linear function. But somewhere in your head, you were doing constant rate of change by subtraction. And so you don't have to explicitly do these steps each time you do it. If you're comfortable, you can do it kind of subconsciously in your head. But as you're developing these skills, it's a good idea to actually start with that question, what kind of function is this? Where are the clues in the sentence? Aha, it's a linear function. And the next step is to write down the general equation for that type of function. So that's y equals mx plus b. And again, you may have already jumped there. That's fine. You did it in your head. I promise you that. Third is name the letters in the equation. Y, M, X, and B. So Y is the distance. M is the slope or the rate of change. X is the time in seconds. And B is the y-intercept or the starting value. And the fourth step is to rewrite, I guess, actually name the letters. Yeah, rewrite the equation with the values that you are given. So y is the distance. We're not given a distance, right? That distance is changing. y stays as a variable. But we know the slope was, let's see, every second gets 2 meters closer. So that's going to be a decrease in 2 meters every second. So the slope is -2. X is the time which changes, and the tiger started 35 meters away. So those would be my steps for writing, building an equation from a verbal representation. Almost always, well, every time that you build your initial equation, your y and your x are going to be left as y and x. Right? What you're really filling in are the m and the b. All right. That's how we do it from a verbal representation. How about a graphical? So here we're going to have a graph of a linear function. I usually have graph paper, and I neglected to bring it this time. So here's, so we go through the same process, actually. What kind of function is this? Well, the graph shows us that's a straight line. So it's a linear function. General equation of a linear function, y equals mx plus b. The y is the vertical. M is the slope, which is the rise over run. X is the horizontal. There's no context here. It's just a picture of a graph, right? This is not the same situation. This is not a tiger in a swimming pool. This is just some graph. And B is the y-intercept. And so now we fill in our equation with what we know. Y equals, I have to figure out the rise over run. Put units there. And there's a couple ways to do it. You could say when x increases by 1, y increases by, it looks like a half. But sometimes the scale makes it a little difficult. So you could also say, well, when x increases by 2, sorry. Oh, goodness. X up by 2, y is up by 1. And those ratios are the same, 1/2 over 1 or 1 over 2. So the rise over run is 1/2. M is 1/2. X, and then the x-intercept, you just look where it crosses the y-axis, which is 2. And that's how you go from a graph to an equation. Anybody have questions about that process? Okay. Tends to be for me, one of the, well, that one's pretty straightforward. Almost always when you see a graph, you're going to see the y-intercept, which is really helpful. And even if the gridding is like, even if it's not a nice, easy step, at some point you're going to have a dot here at the y-intercept and a dot somewhere else on a grid. Right? And you can count over the number of steps and you can count up the number of steps, and that's your rise over your run. Okay. How about a table? Tables can get a little trickier, or the numerical representation. So there's a number of different subtle differences here. The first example might be represented by x goes from 0, 1, 2, and 3. Y goes 3, 7, 11, 15. So your first question is, what type of a function is this? So figure it out. Okay, that goes up by 4. And this one also goes up by 4. It's looking promising. And that one also goes up by 4. Okay, so I'm pretty convinced this represents a linear function. Constant addition, linear function. So let's remind ourselves it's y equals mx plus b. Like I said, sometimes you might end up doing some of this in your head. So I'm going to leave off the y and the x, because what I'm really looking for is the m and the b. And now I can just read off from my table, when x is 0, y is 3. And each time x goes up by 1, y goes up by 4. So I have y equals 4x plus 3. That's your basic, where you get this nice full table that actually shows you your x-intercept, increases by 1 each time. That's not always going to be the case. Sometimes you might get something that looks like x and y, negative 3, 0, 3, 6 for the x, and 10, 8, 6, 4 for the y. So I need to figure out if this is a linear function. It's not changing by 1 each time, but it is changing by 3 each time, the x value. So when x changes by a constant 3, y changes by a constant negative 2. Okay, that's linear. So y equals mx plus b is my formula. M is the rise over run, it's the slope. And when x goes up by 3, y goes down by 2. So that's how I would pull out the slope when it's not just a simple +1 each time. You just say, how much does x go up by? How much does y change? And it's the change in y over the change in x. And fortunately, we still have our y-intercept shown right there. So our line is y equals negative 2/3 x plus 8. And there's one more possibility. There might be 2 or 3 or 4 more possibilities, but one more that I want to tell you. The line goes through the points xy equals -4 and 7, and xy equals, let's see, 6, comma, 22. I think 22 is what I want. Hopefully I built this well. Find an equation of the line. We're still going to do our same process. Step one is, what kind of function is this? Well, it's linear because they told us it's linear. And that means y equals mx plus b is what we need. So we're looking for the m, which is the slope. And we're looking for the b, which is the y-intercept. Unfortunately, neither of our points has x equals 0, so we can't just read off our y-intercept. And I don't have this nice table where I've got regular changes in x each time and regular changes in y each time, but I can still build a table. And it's still going to allow me to get at least the slope. Because if I put -4 here paired with 7, and 6 here paired with 22, I can still do this. How much does x change? How much does y change? X changes by going up 10. Y changes by going up 15. So the slope is the change in y over the change in x, 15 over 10. Now, if you want to write 15 over 10 as a decimal, you could do 1.5 or you could do 3/2. I don't care personally. Any of these three, totally fine with me. Tells you how y changes when x changes. I'm going to use 3/2 because I've trained myself enough to use the reduced fraction for a slope. But again, I don't care. My open math wouldn't care either, I think. They might ask for a reduced fraction, in which case you need it this way. But most of the time, 15 over 10 should be fine. So the question remains, how do we find the y-intercept? And here's where the first time actually in this class, I think, where we need to do a little bit of algebra. We know that y equals mx plus b is our formula, and m is 3/2. We don't know b yet. But we do have some more information. We have an x and a y pair. We know that when y is 7, x is -4. And we still need that plus b there. And this relationship has to be true in order to be on the line. And now we have one unknown. We're looking for b, and so we can solve for b. So doing the arithmetic, we have 7 equals 3/2 times -4 is -6 plus b. Add 6 to both sides. And we get b equals 13. And so our last step is to write our formula, y equals 3/2 x plus 13. And we did it. All right, one more topic, and then I'll hand out the worksheets. That is function notation. And we're going to use linear functions for this. So if we think of the x as determining the y, which we have been, right? We've been thinking about speed determines miles per gallon, and number of weeks determines how much money is in the bank account, and number of seconds determines how close the tiger is. If we think of x as determining the y, we could build a little schematic where we take our x and we put it into this box, and out comes the y. So this box represents the function. Maybe y equals mx plus b. Call this function f for function. Then y, which is mx plus b, is also the function f applied to x. In our notation for applying f to x is f and then a parentheses and then the x. We read this f of x. So now instead of y equals mx plus b, we can write f of x equals mx plus b. Main thing that this allows us to do is to be a little more efficient in asking questions. So let me give you an example. Let y equal negative 3x plus 21. What is y when x equals 2? Well, put x equals 2 in there, and we get y equals 15. Perfectly, I mean, I'm pretty happy with this. If we use our function notation, now we say that f of x equals negative 3x plus 21. Our question becomes a little more compact. It becomes f of 2. What's the function value when the x is 2? The process is the exact same, but our question becomes, instead of 1, 2, 3, 4, 5, 6, 7, about 7 words, it becomes 1 word. So these are the same question. And we would often write this as evaluate f of 2. This means find y when x equals 2. We can ask the other way around. Let's consider our example of the tiger. Starts 35 meters away. Every second gets 2 meters closer. How close is the tiger after 10 seconds? All right, that's like setting up y equals minus 2x plus 35 and asking what is y when x equals 10? Or saying f of x equals negative 2x plus 35 and evaluating f of 10. $15 meters. All right, so these are all the same question. Question 1, question 2, question 3, they are all the same question. How close is a tiger after 10 seconds? I could also ask, how many seconds have passed when the tiger is 25 meters away? Which is saying, what is the x when y equals 25? Right? The y is a distance, so we know y is 25, and what is the x? Which is equivalent to asking, solve f of x equals 25. Find the x that makes the output equal 25. And this is most easily done using the y equals mx plus b. Y equals negative 2x plus 35. Those three questions are the same. We know y is 25. And we're going to solve for x. First thing we do is we subtract 35 from both sides. And we get negative 10 equals negative 2x. And then we divide both sides by negative 2. And we get 5 equals x. And so our answer is 5 seconds. So one thing you have to keep clear is the difference between evaluating a function at a certain input